Audio, video. Hello, hello. Welcome everyone to our interdisciplinary software seminar. I just had an amazing meal of mozzarella and bacon, um, pan fried on olive oil and served in French bread. And I'm well stocked with stock chocolate liquor, so I'll have a sip of that. Excuse me. And hopefully I'll be able to get to the end of this video. Well, we're going to do three things. One of them is ponder on the virtues of punctuation, so let's jump right in. Here's a very well punctuated string. I wasn't born of a whistle or milked from a thistle at twilight. No. I was all horns and thorns, sprung out, fully formed, knock-kneed and upright. And down here is the binary data on computer. And let's look at how the computer is punctuating this binary data. So first we have this quotation mark, and that's a 32, a 34, 32 I think is 0, 34 in ASCII, and that's that right there, 34 in ASCII. Well, the first thing we have to ask ourselves is, why are there two zeros right there? That's our punctuation mark. What it means is that, it only takes 6 bits to transmit 34, but we don't care about that because we have to punctuate the data. We have to establish that, this code we're using, it goes like so, and then like so, and then I was going to say 7 bits, and the last one's a parity bit, but that has changed. Like so, and then like so, and then like so, and so forth. So we don't see the parity bit here. So obviously we're not using parity bits, but we're using a lot of leading zeros. And these leading zeros, you can think of them as our punctuation marks, right? Now, the other thing we do for punctuation is we locate where the data begins. And oh, by the way, this is just as a check that this begins with a quotation mark, ends with a quotation mark, and there it is, 34 in ASCII, and there it is, 34 in ASCII. I mean 34 in binary. Now, the way we could think of this is, besides having a specified word size of 8 bits, so that's an implied punctuation right there, which we're rendering with spaces between. I mean, that's just a visual aid. The computer doesn't need spaces. The computer can just count 8 bits, and then it knows that the next 8 bits are different word size. So we have an implied punctuation here. Next, we have to know where the data begins, and that's in a PC, that's done through what is called a file pointer. In C, the C programming language, that's how we would declare it. We would declare something called like text file, and text file is a variable that points to the memory location of the beginning of the data. But in blockchain, the block of data begins. Well, in blockchain, we can think of, if we're looking at this kind of, declaration, we can think of a pointer to a block. Now, what would a pointer to a block be? Well, the block of data begins by listing the bits in the message digest of the previous block of data. That's just given. That's just a given from blockchain. Every time we begin a block of data in blockchain, it lists the bits of the message digest of the previous block of data. So I suppose we can go on a wild goose chase, look for previous blocks of data, find the previous block of data that corresponds to this message digest, and then you're done. You know where to add the block. Since the message digest is a fixed length, we know where the data begins just by skipping. And what I mean by that is that if you want to, the message digest has, I think it's 256 bits. And so if you want to know where's the data in that block, you just skip the 256 bits and go to the beginning of the data. Next thing, well, I think I showed this. And so now we're going to show that blockchain as we understand it is doing more or less the same thing. Let's do that. So in a computer, we have a memory location, that's the file pointer. And we have a memory word size, that would be the 8 bits. In the ASCII example, that would be, 8 bits is the word size. And so this set, together, the memory location and the memory word size, in a way, they are the punctuation. And the blockchain is getting amorphous, but it is still structured. It has an identifier of a previous block, and it has an implied block size, which is, somewhat analogous, very analogous to the memory word size. The identifier of a previous block is obviously somewhat amorphous, but it's analogous to the memory location. But now we're ready to show that there is another way. Chana! Well, it's called the Zeckendorf theorem, or the Zeckendorf representation. And we'll begin by noting, we'll begin by having a sip of, what was that? Where was my chocolate liquor? Oh, here it is. Good. Excuse me. So, binary data is fundamentally just numbers. And here we have the binary code as traditionally understood. We begin with a 1, and then we have a 2, and then we have a 4. This is a geometric progression with 2 as the common ratio. 2 is the ratio, so 32 goes to 64, goes to 128. And just for convenience, I'm doing Big-Endian notation, meaning that, the least significant bits are first. It ends with the big bits, right there, 1024, that's the big bit. It ends, that's Big-Endian notation for you, if you needed the trivia. But here's what we mean by binary data. It's all just numbers. We have either 0, which means the absence of the 1, and then 0, which is the absence of the 2. And then here we have a 1, which means the presence of the 4. Here we have the 0, which means the absence of an 8. Here we have a 1, which means the presence of a 16, and so forth. In other words, this is just a number that evaluates to 4 plus 16 plus 64 plus 128, and that's it. We're done. Oh no, there's a 124 right there. 124. There's the presence of a 1024. Just a second, please. Audio, video, okay. Now, before we go into this business right here, you may be wondering why there's never a 2 here. Why we can write all the numbers with 0s and 1s. And the answer is pretty simple. It's because 2048, which is the next item here, is exactly twice as much as 1024. So we will never need a 2. If we needed twice 1024, we can write a 0 here and a 1 there. If you want to think of a situation where we would use 2s, we can think of a common ratio of 3. So we start with 1, and then we go 3, and then we go 9, and then we go 9 times 3, which is 27. And in this scheme here, we would use 0s, 1s, and 2s. The disadvantage of doing that is that computers are notoriously good. I mean, the electronics is notoriously good at having one state for one voltage and another. One voltage for a 0, another voltage for a 1, and it turns out that 2 voltages is optimal. Now, so we're sticking with 0s and 1s. Okay, we're only going to have 0s and 1s. But what we're going to do is, instead of having a common ratio of 2, like we have here, we're going to have something else going on in these numbers. We're going to have the Fibonacci sequence. So the sum of 1 and 1 is 2. The sum of 1 and 2 is 3. The sum of 3 and 5 is 8. The sum of 5 and 8 is 13, so on and so forths. And we're gonna still have 0s and 1s down here. And if you think about it, these numbers here, these numbers here, they're not quite as large as those. And so we have the ability to represent more numbers than we really need. And the way this is going to show up is, interestingly enough, look at this 13 and look at this 21. Look at this 1 and look at this 1. Whenever we have 2 consecutive 1s, we don't need that, because 2 consecutive Fibonacci numbers always evaluate to the next Fibonacci number. Notice, 13 plus 21 equals 34. So we could always turn this into a 0, this into a 0, and this into a 1. And there, we have our 34. We have our 13 plus 21. We will never need 2 consecutive 1s to represent a number. And what is even better than this is that the result is unique. In other words, remember, we want uniqueness in the sense of the binary code, and this will also give us uniqueness. If we allow 2 consecutive 1s, we allow for non-unique numbers to be represented. But if we disallow 2 consecutive 1s, we're going to say no. We're never going to tolerate 2 consecutive 1s. We're always going to separate this data out. In that case, this gives us a unique code for all the integers from 0 to infinity and whatnot. But what is interesting about this is that we have just gotten ourselves this. 2 1s, consecutive 1s, will never happen. This means that 4 1s will never happen. And 6 1s. Any even power of 2 will never happen. These can be thought of as punctuation marks. we can use these, in fact, for punctuation marks. What we mean is that the data, the ordinary data, which we will treat as either numbers or just some redefined code, is going to be whatever doesn't have two consecutive ones. Let's see if we can make this a little clear. So here we start with a 0. We have two consecutive ones. That cannot be. That's a punctuation mark right there. Let's replace that by P. And then we have a 1, a 0, we have a 1, a 0, a 0. Oops, two consecutive ones. That's a punctuation mark, P. Now here we have two consecutive ones. That's a punctuation mark. Here we have, well, let's just do this one. And here we have 4 consecutive ones. Well, 2 consecutive ones is a punctuation mark. And then 2 consecutive ones is a punctuation mark. So our punctuation marks consists of P's. You know, PP is a punctuation mark. PPP is another punctuation mark, as long as, you know, it's all it's all sequential. They could have different interpretations. And you might think that if, worst case scenario, let's say we're transmitting really large numbers. So we have a really large number, and then we have a 1, 1 to indicate that we're dealing with another large number. Then we have another really large number. Well, if this is the case, you might think that this code is very wasteful, because in order to represent a really large number, it would take too many bits. But guess what? This is not the case. It turns out that we can figure out how many bits we need to represent large numbers with this code. So there it is. I did the math for you. It's not rocket science. It isn't like we're trying to figure out the year when global industrial civilization is going to collapse or anything complicated like that. And it turns out, in the limit of large numbers, we will only need 10 bits for every 7 bits in binary. And, that's not too bad.